Ever felt like you're looking at some complex digital design and, I don't know, just wishing you had a way to instantly grasp what's going on underneath?
Or maybe you're just fascinated by how computers actually see things, how they
Yeah.
handle visual stuff.
Yeah, exactly. Well, think of this as your shortcut. Welcome to the deep dive. We dig through source material to pull out the really essential insights for you.
And today, we're diving into something pretty fundamental in computational design: pixel and voxel data structures.
Right. You've probably heard of pixels, those tiny dots
Sure.
on your screen. Yeah, like a 2D grid.
Mm-hmm. And voxels are, well, kind of their 3D cousins. Think little cubes making up shapes in 3D space.
Yeah,
Understanding these is really key to getting how computational design works.
totally. And to figure this out, we've looked at some great stuff recordings from the 2025 Data in Design Class '09 workshop, both parts 1 and 2.
Plus the briefing docs for that workshop. And interestingly, they were in both English and Korean, which kind of shows how universal these ideas are becoming.
Good point. So our mission here is to really pull out the core ideas. How are pixels and voxels actually used in design? We want those aha moments for you without getting lost in, super technical jargon.
Exactly. I'm here to help synthesize all that and give you the context you need.
Okay, let's jump right in then. One thing that really stood out from the workshop was this emphasis on connectivity and data smoothing.
Oh, yeah, that came up again and again.
The instructor even said, let me find the quote here. This is the most important thing for the Pixel and Booko data structure.
Yeah.
So how we smooth the data, like basically smooth this pixel around their neighbor so that we can affect the information throughout the boxes.
And that concept of connectivity, how each pixel or voxel relates to the ones right next to it is, well, it's everything.
So like for a pixel, it knows about the ones above, below, left, right, maybe diagonals too.
Yeah, exactly. It could be 4-way or 8-way connectivity. And then in 3D, for voxels, it just extends out front, back, top, bottom, sides. This network idea is fundamental.
Okay, and then smoothing. That sounds like you're sort of blurring the data, making transitions less harsh.
That's a good way to put it. Imagine one pixel has a certain value, maybe a color. Smoothing lets that value kind of bleed into its neighbors.
Yeah.
Like the instructor compared it to a convolutional filter, like in image processing. When you blur a photo, each pixel becomes a bit like the average of itself and its neighbor.
Right. That neighborhood influence thing.
Exactly. It's about propagating information through that connected grid.
So if I change one pixel's color dramatically, smoothing would help that change sort of blend outwards gently.
Precisely. And as they show later, you can control how fast and how far that influence spreads. You can run the smoothing process multiple times or use like scaling factors to make the neighbors more or less influential.
Got it. So these grids are connected and data can flow across them. Let's maybe break down the structures themselves a bit more. Pixels first.
Sure. So at its core, a pixel needs its position, right? X and Y coordinates. Maybe Z if you're dealing with layers, like in Photoshop.
Yeah.
But crucially, it also contains that neighbor info, the connectivity we talked about, and it can hold metadata. That's basically any other useful information you want to attach to that specific spot on the grid.
So like temperature data at
Yep.
that point, or material type.
Could be anything, yeah. And a whole collection of these pixels organized, that's your pixel map. It's a different way of thinking about images or spatial data, not just pictures, but grids of interconnected data points.
And voxels just take that into the third dimension.
Pretty much. You've got XYZ coordinates for
Mhm.
position in a 3D grid. You've got connectivity to neighbors in 3D. And you've got metadata storage.
Okay.
The workshop had that bunny shape example, which was quite good.
Hmm.
They took a standard 3D model, just the surface mesh, and turned it into voxels.
What did that show?
Well, it showed how you represent the volume. But interestingly, the inside of the bunny, since it wasn't defined by the surface, ended up hollow in the voxel version. So it highlights how voxels represent volume, or maybe the absence of it.
I see. Okay, so those are the building blocks. How do we actually see these used in, like, real design work? The workshop mentioned quite a few things.
Yeah, they're surprisingly versatile. Terrain modeling is a classic one. Digital elevation models, DEMs, they're basically pixel or voxel grids where the data value is height.
Right, like a height map.
Exactly. And once you have that grid, you can calculate stuff like the slope at any point just by comparing a pixel's height to its neighbors. Or they mention using luminous information, maybe simulating light, to visualize the terrain better.
So you can analyze the form directly from the grid data. That's powerful.
Definitely. And another big use is just visualizing any kind of data spatially. They showed mapping color to data values in the grid.
You mentioned changing one pixel's color.
Right, and then you could actually watch the smoothing happen, see the color diffuse outwards. It makes that abstract idea of data flow really concrete.
It does, yeah. What about getting specific information out of these grids, like querying?
Yeah, that's key too. You can ask spatial questions like, find me the voxel closest to this specific point in space. They showed that Live and Grasshopper moved a point around and the nearest voxel lit up.
Oh, cool. Dynamic feedback.
Or you can query based on the data itself. There was another demo where they scattered random points across a grid, then each cell was colored based on how many points landed inside it.
So like a density map.
Exactly. A basic kind of spatial analysis, seeing where the data clusters.
Okay, so you're representing space, but also analyzing what's in that space.
Precisely. And to kind of drive this home, the workshop assignment was interesting. It asked people to look at existing designs and think about how they could be represented using pixels, voxels, or even graph structures.
So learning to abstract real-world stuff into these data models?
Yeah, exactly. It's about developing that computational way of seeing things. It's a really important skill.
Makes sense. They also mentioned ontologies and object-oriented programming, OOP. Sounds a bit more technical.
It is, a little, but it's really about managing complexity. Think of an ontology as just like a structured way to organize your knowledge. What kinds of data do you have? How do they relate?
Okay.
And OOP gives you the tools in programming to build that structure. You define classes like a pixel class that knows its own color and position, or a voxel class maybe with dimensions and material. It just helps you manage lots of data cleanly.
So it stops things getting messy when the data sets get huge.
Pretty much. You need that kind of structure for real-world problems.
Right. Okay, shifting gears a bit. The workshop also talked about remote sensing and images, seeing the world through data.
Yeah, that's a natural fit. Satellite images, they're fundamentally pixel grids, right? Each pixel holds data about a patch of the Earth, often in different light frequencies. They mentioned the vegetation index. That's where you analyze like the intensity of red versus infrared light in the pixels to figure out how healthy the plants are down below.
Wow. So you turn image data into environmental insight. What about just like normal photos?
Any digital image is a pixel map. And once you think of it in that way, you can apply all sorts of image processing techniques, resizing obviously, but also blurring.
Which is like the smoothing we talked about.
Exactly, using that neighborhood info.
Oh,
Or edge detection to find boundaries, and just manipulating colors. They showed some fun examples like blending an elephant and a rabbit.
okay.
Or inverting colors, which can sometimes make subtle details pop out. That's actually used in remote sensing too, to highlight specific things.
Huh. Never thought of image editing quite like that. And you can pull these images into design tools like Grasshopper.
Yeah, they showed importing images just using a web link.
Yeah.
And the cool part is linking the pixel data, like brightness, to geometry. So bright pixels make tall points, dark pixels make low points.
And you get a 3D height map straight from a 2D image.
Exactly, super useful technique.
Very clever. They also use this kind of grid data for environmental stuff, right? Simulating the sun.
Yeah, that was a great example. Using environment tools in Grasshopper, you can figure out the sun's position in the sky at any time for any location.
The sun vector, they called it.
Right, the direction to the sun. And then you can project that onto your pixel grid or terrain model and see which pixels are getting direct sunlight and which are in shadow.
And you could do that over a whole day or year.
Yep. Track the sun hour by hour, day by day, see which parts get the most sun overall. Really useful for architects thinking about light, heat gain.
Or where to put solar panels.
For sure. And they even showed extending it to 3D voxels. You could visualize like the volume of space around a building that stays shaded all year round. Gives you real design insights.
Man, these are such varied uses. It really brings home something the instructor kept saying, the need to understand the basics, and this idea of reinvention.
Oh, absolutely. He really hammered on needing to get the fundamentals of programming loops, calculating distance, working with ranges, the building blocks.
If you don't understand the front part, you won't understand the back part, was the quote, I think.
That's the one. You can't just jump to the fancy stuff without grasping how it actually works underneath.
It connects to reinventing the wheel. Normally that sounds bad, like wasting time.
Right. But his point was, in computational design, maybe it's good. By really digging into basic concepts, color theory, how things are made, whatever, and trying to rebuild them yourself.
You understand them so deeply that you actually find new ways to do things.
Exactly. It's not just copying, it's deep learning that can lead to real innovation, especially because the field itself is always changing.
That's a much more positive spin. It's about mastery, not just repetition. He told that story about the BIM hackathon, too.
Yeah, about seeing someone present who seemed impressive but maybe didn't fully grasp the how behind their results. They could use the tool but not explain the core principles.
So it highlights the danger of just surface-level knowledge.
And the value of really building that solid foundation for the long run.
Okay, that deep understanding seems critical. Now, there were also lots of practical Grasshopper demos shown. Can you quickly recap some key ones?
Sure. Well, they showed setting up a basic pixel grid, just defining the corners and how many divisions you want in X and Y. Simple, but fundamental.
Visualizing it as points, too, right?
Yeah, seeing
Yeah.
the grid structure
Yeah.
and identifying neighbors, how each cell connects. They touched on the idea of grids wrapping around, like Pac-Man, though didn't fully build it out.
Okay, and 3D.
Creating a voxel grid just by defining its size in 3D space. And the querying we mentioned, finding the closest voxel to a moving point.
Yeah, the dynamic highlighting.
And the random points,
Right.
example, scattering points and coloring cells based on how many they contained. A nice visual way to see data density.
What about the coding side? Python.
Yeah, they stressed using Python in Grasshopper.
Huh.
Showed making a custom pixel class and passing that complex data between different script components. It really helps organize bigger projects.
More modular.
Exactly. And importing images, like we discussed from the web or your computer, and turning pixel brightness into mesh height for those height maps. The world map example was pretty clear.
Right. And all the image processing tools.
Yeah, a whole suite within Grasshopper. Resizing, finding colors, isolating color ranges, blending images different ways like darken mode inverting, adjusting brightness, contrast,
That was
saturation.
little source.
Blur, sharpen, edge detection, using specific methods like the Roberts cross operator. Lots of standard image processing stuff, but applied within a design context.
And finally, the solar analysis, calculating those sun vectors and shadows.
Right, showing how light would hit a grid or a 3D form over time, a direct environmental application.
It's amazing how these simple grids support so much. Did they look ahead at all towards the future?
Briefly, yeah. Mention an upcoming session on AI and design. The key points seem to be you need the kind of foundational understanding we've been talking about today to know where AI fits in.
Like, what problems is AI actually good for, and what isn't it?
Exactly. He referenced Andrej Karpathy's ideas about software 1.0 versus 2.0, framing how AI is changing development. And just a reminder that big breakthroughs take time and consistent effort.
Like the Messi, Ronaldo, Elon Musk, NASA examples.
Yeah. It's a long game, which kind of loops back to that idea of reinvention being about continuous learning and adapting, especially as computational tools evolve so fast.
Okay, so wrapping up this deep dive, what's the main thing you want people listening to take away about pixels and voxels?
I think the core idea is that they're not just, technical terms. They are fundamental ways of thinking about space and data in design, focusing on how these little elements connectivity and how information flows and refines through them. Smoothing opens up totally new ways to represent, analyze, and even generate designs based on data.
They're truly foundational tools.
Absolutely. And getting that solid understanding, embracing that idea of really exploring and maybe reinventing things for yourself. That's what unlocks the real power.
Couldn't agree more. So here's a final thought for you, the listener. Pick an object, any object, or maybe a space you know well. How could you start to imagine it as a grid, pixels or voxels? What data would each little block hold?
It's a fascinating exercise, right? It can really shift how you see things.
Definitely. We really encourage you to explore these ideas more. Check out the examples if you can. Thanks for joining us on The Deep Dive.